Right. Good afternoon. Welcome to the lecture of the elementary principles of chemical processes. Today, we will still talk about one single phase system, and which is we want to know about the specification in gas, liquid, and solid. So on Monday, uh, we know that in chapter 5, we want to determine the variables physical properties and use them to derive additional relations, right? Additional relations means what? Specification in the degree of freedom, right? In the DOF. And so there are three methods to find out the variables. First one is check the data, right? First one, check, find the books and get the answer. This is one. The second one is that if you have a combination of a mixture, that means it makes things more complicated. For example, if you want to check uh, the density of species A, then you can find out from the book. But if you want to find out the density of a mixture which containing 55% mixture A and 55, that means if another 45 B, the density of this mixture, then that will be not easy to find from the books because you have hundred and thousand combinations. So it is difficult for you to find out. So that means what? That means it's impossible to find out this. So you have to estimate. You have to estimate. So there are some of the equations, or you can do empirical correlations to find out the property. Okay. So this second method. The third method is what? To do the experiment to measure the properties. For example, if you want to find out the density of a mixture which containing 55% A and 45% B, you just measure it, right? You measure the volume, measure the weight, and you got a density. Okay, so this is the third method. So first of all, on Monday we talk about the densities in the form in liquid and solid, and we understand um, for the solid and liquid, it doesn't change too much. So because in order to know the density, because the mass doesn't change in liquid or solid. So but value changed because of temperature, okay, or because they mix together. So we have two methods. One is called value additivity. You add up values, and this is one of methods to measure the mixture, the density of the mixture. Okay, and second one is called fraction of density. They use the rules, they use the mass and use the fraction. So there are two methods to get the answer of the density. Okay, and we give you an example. Uh, we give you an example which is in the end here. This is one. So from the mixture of the what? The mixture of the H2SO4, if I remember it right. Yeah, 50% H2SO4 by weight, and together with 50% H2O by weight at 20 Celsius, and you want to know the density. So first of all, you check out from the Paris Chemical Engineering Handbook. So you get this answer, which is very correct, very close to the right answer, right? And then you use two different methods. Estimate it. You use value additivity, okay? And you use the average density. Average density means what? The fraction of the density. So these are the three answers you get from different methods. Okay. So as we know that because 1.3952 is more close to the true answer. So as you can see from this mixture, the fraction of density is more close to the correct answer. Okay. So this one telling you what? This method telling what? This method is more appropriate for that mixture. Okay. So today we want to move to the density of the gas. Okay. And first of all, the section 5.2 is ideal gases. So if you think of ideal gases, they must have non-ideal gases, right? But first of all, let's talk about the simple case first, which is ideal gases. But before we talk about gases, so ideal gases is what? The density of a solid or liquid doesn't change a lot while temperature and pressure change. It doesn't influence a lot, but the density of the gases follow a P pressure, volume, and temperature relations. Okay, as you know, this is what we call PV equal to nRT, right? PV equal to nRT. So this cartoon showing you that this, if this red sphere, red ball represent a single atom, and then the single atom packed very well. As you can see, this is what? This looks like a solid, a solid. However, if the atom doesn't pack that well and randomly dispersed in a container, and this one looks like what? This one looks like a liquid phase. The atom in the liquid phase, right? Liquid. And how about this one? This one, the distance between atoms to each other are very far away. And this is what we call, this atom is in the gas phase, right? In the gas phase. So the density of this material in a solid form will be larger than the density of this material in the liquid form will be larger than the density of this material in the gas form or gas phase, right? Okay. So in the gas, we think we are talking about vapor, volume, pressure, and the temperature, right? So in 2 centuries ago, there are many scientists study on this case. For example, I'm sure you all know this, that Boyle's law means what? If you keep more mass and the temperature as a constant, and then you change the volume, and you find out the volume inversely proportional to the pressure. What does that mean? If you have a more and temperature as a constant, you decrease the volume, that pressure increased. And then if the volume increases, pressure decreases. So what does that mean? Inversely proportional, right? Inversely proportional. Okay, so something increased and you will cause something decreased. Okay, so this is called Boyle's law. So relationship between volume and pressure. And Charles' law is what? Charles' law is keep the more and the pressure as a constant, and you change the volume and the temperature. So if you lower the temperature, you realize volume decreases. Okay, and you increase the temperature, and you realize volume increases. Okay, this is common sense at this moment, right? In this time, because we learn this a lot when you are in high school or junior high school. And also, Amonton's law. Amonton's law is you keep more and the volume as constant, and you want to know the relationship between pressure and temperature. Again, if you lower the pressure, the temperature decreases. And if you higher the pressure, the temperature increases. Okay? And Avogadro's law, you keep temperature and the pressure as constant. You want to know the distance, the relationship between moles and the volume. Again, you realize something. So if we put these laws together, we realize Boyle's law, pressure and temperature, they are proportionally inversely proportional, right? So P times V will equal to a what? A constant, because it's inversely proportional, right? It's equal to a constant if N and T is a constant, right? We use K, and Charles' law realized that V divided by T will be a constant. We call it K prime. Again, Avogadro's law tells us that V divided by N will be another constant, which is we write down K double prime. So as you know, if this here is all a constant, and let's put it together, that'll be what? That'll be P times V divided by NT will become another constant, right? Okay, and this is what we call Mendeleev. In 2 centuries ago, he realized this, and then he wrote down a very famous equation, PV equal to nRT. This is what we call ideal gas equation of state, ladies and gentlemen. Ideal gas equation of state. You know this when you are young, right? Okay, but this is a very important equation, and you know that this is ideal gas. This equation is especially for ideal gases only. Okay? So expression and the condition for the ideal gas, you know, is ideal. So you know that you need to give some conditions for this ideal, right? So equation of state we call 状态方程式 in Chinese is the relationship between what? This equation of state is relation with different states, like mole quantities and the volume of the gases and the temperature and pressure. So ideal gas equation of state is PV equal to nRT. So there are many different equation of state. You can have a non-ideal equation of state. And this is ideal gas equation of state. So in chapter 5, you will learn a lot of equation of state. The most importantly and basically, PV equal to nRT is the one you need to know. So what's the condition for ideal gases? You have ideal gases, that means you might have some conditions for non-ideal gases. So for the ideal gas, is that ideal gas need to be in the high temperature. How high? 0 Celsius. You know, 0 Celsius is 0 Celsius. If the temperature above 0 Celsius, which is 273.15 Kelvin, right? 0 Celsius. If this above 0 Celsius and it's more close, it's very likely to be this kind of condition. The gas in this condition should be in ideal gas. Not only this, but also low pressure. Low pressure. What's the pressure? What's the borderline? 1 atm at room temperature and at the atmosphere. Okay, ambient condition, which is 1 atm. Okay, so if you have high temperature and a low pressure, normally PV equal to nRT can be used for most of the gases. You might think, Professor, does it make sense? Does it make sense? Yes, it makes sense because high temperature means what? As I told you, that the high temperature means that if you have a sum of the substance, if you have a higher temperature, that means it's easier to become a gas. Why? Because you decrease temperature, the material will change the form from gas to liquid to solid, right? If you think of the water, right? Water above 100 Celsius, for example, 200 Celsius is in the water is in the steam, right? It's vapor, and you reduce the temperature. I should say that let's say water. In case of water, if your temperature is below 0 Celsius, that means what is in solid, right? If you increase the temperature to 10 Celsius, it becomes water, right? And if you increase the temperature up about 100, it becomes vapor. So if you have a higher temperature, that means it's easier to become gas. That's why we say that a higher temperature means it's 0 Celsius, above 0 Celsius. And low pressure is below 1 atm. Why? Because if you have low pressure means what? If you think of the concentration or the density, if you think of density, low pressure means in this cube, there's less atom or molecules. That means it's low pressure. If you have high pressure, that means what? This cube will have more atoms. That means high pressure, right? Low pressure means you have less atoms. So the interaction of the atoms will be less. That means it's easier to become a gas. So I don't think this is difficult for you to realize high temperature and low pressure. Okay? So you better think, if I give you a number, and you better think, is this easy to, can you use this can you use this condition to regard as ideal gas condition or not? Okay, high temperature and low pressure. Right, so let me write down this for you. So low pressure, if you have a low temperature less than 0 Celsius and high pressure, PV equal to nRT doesn't work because this is not regarded as an ideal gas equational. You cannot use ideal gas equational state because this is not an ideal gas. Okay? Right. So let's move to ideal gas equational state. So the assumption of the ideal gas equational state is, or assumption of the ideal gas equation is that the ideal gas equation of the state can be derived from the kinetic theory of the gases by assuming that what? So if you can, if you want to assume, you can have assumption. Okay, there are three assumptions. The first one is the gas molecule has a negligible volume. That means what? This gas, we regard the gas has no volume. Okay, we regard the value of the gas. There's no value of the molecule. First one. The second one is inert no forces on one another. So there's no energy exchange between the molecules. But as a matter of fact, the molecules will hit each other, right? Well, collisions. But we assume there's no energy exchange. There's no forces on one another. Okay, this we regard this as ideal gases. Okay, the third condition is collide electrically with the walls of their containers. That means this atom hit the walls without any energy exchange. It's elastically. So there's no energy loss. Actually, if you have high pressure, this wall will get energy from molecules. That's non-ideal gas. Ideal gas is that you don't have energy exchange. The wall doesn't receive any energy. I mean, in terms of the heat, right? In terms of the heat. Okay? So these are the three assumptions for the ideal gas equation. Okay? So this ideal gas will have no volume and will have no interactions between each other. There's no force, there's no energy exchange. Okay? And also the molecular hit the wall and there's no they don't develop energy to the wall. Okay? So these three, I want you to remember these three. Okay? And also the previous page, I want you to remember high temperature and low pressure. Okay? Right. So now I want to show you some of the things which you haven't learned when you are in high school. So we know PV equal to nRT, right? Have you heard about P over dot equal to N over dot RT? Over dot means what? You divide value divided by time. That means what? Volumetric flow rate. N over dot means what? N divided by time. That means what? Molar flow rate. Okay, so we are talking about a continuous process or we can draw a flow chart to represent P V over dot equal to N over dot R and T. Okay? So I don't want to waste your time here, so I just let you know that this is a very easy to remember. If you divide it by time here, divide it by time here, you will have this equation. So equation can also be expressed as what? As P over Kara equal to RT. Because N is the mole. So if you put mole, if you have value divided by mole, this is called V Karas. Why we need to do this? Because this can be we can call this a specific molar value. How many values per 1 mole? So this is called V over the Karak. How many moles, how many values per 1 mole? Okay, So this is called specific molar volume. So you simplify PV equal to NRP, PV equal to NRT to become like this. And this makes sense, and this is more easy to use because V over Kra is value per mole, value per mole. Okay, and also this is called specific molar volumetric flow rate. If you have over that, if you have a over that here, that means the flow rate. Okay. Right. So again, a gas whose PVT behaviors is well presented by PV equal to nRT equation is said to be have as an ideal gas or a perfect gas. We always regard it as an ideal gas. Okay. So what's R? R is a gas constant. I hope you know that gas constant. So you can get the gas constant with different units from SI unit, CGS unit, or American engineering unit, American engineering system, sorry. So different system got different gas constant. Okay? And I'm sure you know this when you're in high school. Right. So now let's think of if this is not an ideal gas. So we cannot use ideal gas equational state. But so far you just learn ideal gas equational state. So if you put the temperature, you put a volume, you put a pressure into this equational state, and you know this is not equation. This situation is not an ideal gas situation or condition. So you want to know how far this condition away from the ideal gas. So this is what we call error in estimate volume. So use epsilon. Epsilon. It's kind of error is estimate value. So in Chinese is that you want to know how far this condition away from the ideal gas. Okay, this kind of gases in this condition and is away from the ideal gas condition and how far. That's what you want to know. So you use epsilon. Epsilon is what? It's X ideal minus X true divided by X true times 100%. So you know that what is X? X can be pressure, can be temperature, can be mole, can be volume. So once you got a value, and then you know that ideal value in the ideal gas condition. So you can use this equation. Okay. Generally, if the epsilon absolute volume is less than 1%, this is less than 1%, we regard this gas is an ideal gas. It's more than 1%. I mean, minus plus 1%. You know, you have absolute volume here. So it's more than 1% or less than minus 1%. This kind of gases doesn't regard as an ideal gas in this condition, in a condition we get. Yes, please. True. 哪边有 true 呢？哦 ，true 是测量的 ，true 是测量的。OK。那 ideal 是这个真实的，我们等一下会有例子，好。Okay, so ideal gas behavior is that if ideal over Kra, ideal specific molar volume is RT divided by P, right? Right? This is another expression is that if you got an answer and then you realize the V over Kra ideal is equal to RT divided by P, and then if this is the container or this condition is that this container containing diatomic gases, which is we call diatomic gases means 双原子, for example, like oxygen, like nitrogen. It's not argon or helium, it's oxygen or nitrogen. These kind of things, if your V over Kra ideal is larger than 5 liter per mole, and this will be regarded as ideal gas behavior. Okay, or For other molecules like ammonium, like methanol vapor, that means if you the V idea over Cara is 20 liter per mole, and this is more than this, it can be regarded as an ideal gas behavior. Okay. So in that case, the absolute epsilon absolute volume will be less than 1, maybe expected. So if you get this, and normally we can regard this as an ideal gas behavior. And then when you calculate the epsilon, normally it's less than 1. But this is normal case. Okay, you really need to do. We have some equations which is for non-ideal gas, and that will be different if you do the calculation, and then you can do the comparison. Okay, using non-ideal gas equational state and also non-ideal gas equational state. Right. Okay. So this is called ideal gas behavior. Right. So now we finish the introduction of the ideal gas equational state, and now let's think of the density of a gas or a mixture, a gas mixture. So we all already know how to measure or how to get the answer of the mixture of the in the solid or mixture of the liquid, right? The density. So how about the density of a gas? So we know that the density of gas again is mass divided by what? Divided by volume. That's everybody knows, right? So if you divide, if the mass divided by a mole, and then volume divided by mole, that means what? That means you will have this is what? This is, you will get average, right? M over bar means what? The average molecular weight, right? Because you have mass divided by mole, that means what? You got molecular weight. And especially this, if it's the mixture, that means the average molecular weight, right? Okay, and if the volume divided by mole, that means what? That means you have a specific molar volume, right? Okay, so if you do this, and you realize this can be what? If you have this volume over dot, and you combine with the previous equation, P times V over K equal to what? RT. So you put a V over K here, P divided by RT, and M here. So you will realize the density will become pressure times average molecular weight divided by gas constant times temperature. So as you know, PM equal to DRT. D stands for density. So once you want to know the density of the gas, you can realize you can use pressure and the molecular weight, or it can be average molecular weight equal to what? Density times gas constant times temperature. Okay? Right. So this is not difficult. Just want to let you know how to measure, how to get the answer of the density in solid, liquid, and gas. Right. So now let's practice. Let's do a practice. Example 5.2-1. Ideal gas equation of state. Okay. So now we have 100 grams nitrogen is stored in a container at 23 Celsius and 3.00 psig. Ask the volume in liter. Okay, can you get an answer for me? Yes, you can, right? Because you know, if you know the molecular weight, you know the gram, so you know the mole. And you know, PV equal to nRT, the Celsius need to change to Kelvin. And this is 3 psig. This is American engineering system, right? So you need to change to ATM. And here I just want to let you know, be careful. PSIG and PSIA. G for gauge, A for absolute. So once you want to use PV equal to nRT, you use gauge pressure or absolute pressure. Which one? Absolute pressure, right? So now in our environment, that's 1 atm. But when you have gauge, that will go to the gauge pressure will go to 0. Why? Because absolute pressure equal to gauge pressure plus 1 atm. I hope you still remember. We talked about this before midterm exam, right? So this that means 3.0 psig means how many psia? How many? You have plus because 1 atm equal to 14.7 psi. So the pressure will be more a little bit higher than the 1 atm. Okay. And then if you do this calculation, you will realize you can get the answer of the volume. And then now the question is verify the ideal gas equation is good approximation for the given condition or not. So we got a volume. So we want to know this volume. We want to know epsilon. Epsilon. Okay? Epsilon. If you use PV equal to nRT, and how to get an answer. Okay, so P is 3 psig, right? Gauge. So 3s. I just want to show you here. Can you see these two gauges? This gauge is the unit of the gauge is psig. So if the pointer go to 0, what does that mean? Is this a 0 vacuum condition? No, because this is what we call 1 atm or 14.7 psi. It's 1 atm. If this go to the psia, if you put this in this environment, this gauge will the pointer will go to 14.7. So this is atmospheric pressure, right? Okay. So if you have these two gauges and then you put it here right now, pointer for PHIG will go into 0, and for the gauge which has a PSIA unit will go to 14.7. So you know PV equal to nRT. You want to know that you want to get absolute pressure. So here is the 1.2 atm. So once you do the N will be what? You know, 100 grams divided by 28 grams per mole. So you have 3.57 moles. So you know that, and then you know the temperature, you know the pressure. PV equal to nRT. So the value you get is what? Is 72.25. So this is nitrogen, right? This is nitrogen. So we have I just told you that how to judge this is ideal or not. This is ideal or not. Ideal is that if you have ideal, you got 20.2 liter per mole, and it's larger than 5 liter per mole. So this is nitrogen, right? So we know that this condition, this nitrogen, the nitrogen molecules in this condition can be regarded as ideal gases. So ideal gas equation of the state would yield an error of less than 1%. Okay? Normally. Right. So, okay, so let's move to the 5.2b, standard temperature and pressure. Is there any way to avoid using the volume of the gas constant? Do you know how to avoid to use gas constant? That's if we have a standard condition for gases, we use that as a standard. So we don't need to remember the constant R. So as you know, that the standard, T standard, T sub S, S stand for standard, P sub S, S stand for standard, okay? So for the SI system, you know that the standard temperature will be 0 Kelvin, 0 Celsius, which is 273.15 Kelvin, right? And 1 atm. And the value will be what? For SI system will be this 0.022415 cubic meter. For the CGS, it will be 22 22.415 liter. And for the moles, standard will be 1 mole, right? Okay. I normally don't try to remember this, but if you want to, this is the American engineering system. So use this standard, we can use this standard to compare to the non-standard condition, and we can remove the R in the calculation. Okay, so the standard temperature and pressure is that what? So the ideal equation of state, PV equal to nRT, is equation 1, right? So this any condition. But for the standard, as a STP, standard temperature and pressure, that means what? You have TS and PS. So we put this together, PS, VS, because N is, we regard N as 1 mole, right? Because this is standard condition. So equal to R times TS. So this is equation 2. So if we put the equation 1 and equation 2 together, that will be what? That will become P times V divided by PS times VS equal to N TS divided by TS. T divided by TS. So we remove what? We remove R, gas constant. You might say, wow, Professor, why we need to do this? Because I'll give you an example very soon. Because sometimes you cannot use PV equal to nRT as you like, okay? So the point here is that no gas constant, okay, in this equation, if you have a standard condition to be a references, okay? So no need to remember R constant in different units, okay? In different unit means what? SI system, American Engineering System, or CGS system. And the PVT knows by different systems, as we know that, okay? Okay, no need R to calculate pressure, volume, mole, or temperature. Right, so here, I just want to let you know that some terms it's not difficult to remember, okay? So there are some terms here. STP stand for what? Standard temperature and pressure, which is 273 Kelvin and 1 atm. How about SCM? SCM stands for standard cubic meter. Okay, and it's meter, right? So it's SI system. So it's 0.022415 cubic meter. How about this? I'm sure you know that now. Standard cubic, F stands for feet, cubic feet. Okay, and how about this? Standard cubic meter, right? Standard cubic meter per hour. So this is kind of related to the flow rate. Especially here is the volumetric flow rate, right? Okay. So when you see the exam, when you see this question in the exam paper, if you see the STP, you know this is standard temperature and pressure. If you see that it's SCMH, that will be standard cubic meter per hour. Right. Okay, so let me see that whether we still. So now let's take a look of this example. 5.2-2 conversion from a standard condition. So the butane, this substance is in a condition of temperature 360 Celsius, and pressure is 3 atm, and the flow rate is 1100 kilogram per hour. So the flow rate means what? The mass, right? The mass. Okay, so you need to convert the mass to the what? To the mole, right? So you change from the mass flow rate to become molar flow rate, and then they want to ask you the volumetric flow rate. Okay, so what's the volume? what's the value or volumetric flow rate. So this is easy, right? So you have temperature, pressure, and you have mole, and PV equal to nRT as long as you know the gas constant, the value of the gas constant, so you can get a value. You can get the volume, right? So P, but if you don't know the gas constant and you just know that the standard pressure, standard volume, and the standard temperature, so you also can get the answer, right? So 3 times volume equal to volumetric flow rate. Sorry, PS is 1 atm and VS is 0.0224. If you remember this, and if you get the number of this 1100, right? 1100, and you got molecular weight, and you put this in, you put the temperature, and your standard temperature is 273.15. Okay, so this is SI system. So I'm sure you got an answer, right? You got an answer. Not difficult at all. Using regardless of the gas constant, you can use this equation to get an answer. Okay, so next example is 5.2-3, effect of the temperature and pressure on volumetric flow rate. So now, do I need to read this? I hope I don't need to read this. It's in the page 2-3. Okay, good. We don't need to read this. So I want to tell you is that we have air into this process, and then the volumetric flow rate is 10 cubic feet, or it can be per hour or per minute, whatever. And then at the condition of 70 Fahrenheit, and then 1 atm. So this kind of air fed into the process and come out with what? Come out with 610 Fahrenheit and then 2.5 atm. And now, what's the value of this? What's the value? Easy, right? Because you know input equal to output. So if you use PV equal, so input equal to input is P1 V1 RT1, right? And output is P2 V2 divided by RT2. And input, more of input equal to more output. So as you can see that, you just use this equation so you can get an answer of the volume. Okay? So there's no problem. This is the answer you got. Easy. Right. And next one is a kind of challenge one. So I want you to realize why we need to do this, why we need to do standard temperature and pressure. That's because we have some problems with the measurements in some rigid conditions. Okay, so this is called convert standard states, PV, PTV, to true states, PTV. Okay, in the page 195. But here, I just want to tell you a story easier for you to understand. For example, in the process unit, this process is 150 Celsius, and pressure is 2.5 atm. And at this moment, we want to know that what's the volumetric flow rate in this process. So again, you have 3 ways to find the answer. One is check the book, check the handbook, right? The Bibles, chemical engineering handbook. Second, estimate. Okay. The third one is what? To measure it. Okay. If you think of the third one, can we measure the volumetric flow rate in this condition? Yes, you can, as long as you have a very good flow rate meter. Okay, because what? Because temperature is very high and pressure is a little bit high. So you cannot get an easy and cheap sensor to put it in to measure the flow rate. In that case, we still want to know what's the condition, what's the volumetric flow rate inside. In this case, we need to measure it outside and then to to think of what's the condition inside. So we have gas in and gas out. And then the volumetric flow rate, we don't know. But we can calculate, we can estimate it by what? By have a condition which is a standard condition, 0 Celsius and 1 atm. And at this moment, at this point, we can have what? We can have a very cheap flow rate meter in this place, and we can measure the volumetric flow rate. So PV equal to nRT. We can find out the volumetric flow rate here. Okay, so how can we do that? As long as we have a value and we know the volumetric flow rate. Standard one is 23.8 standard cubic meter per hour. That's what we know. And if we know that, if we can measure the flow rate in this place, that means we know the moles, because input equal to output, input equal to output. So the input per the mass goes through this will be equal to the mass goes through this. And again, we know that in this process, mass A will equal to mass B. That's what we need to know. So important thing is we need to know the mass in this flow rate. What's the mass flow rate here? And we can invert this to the mass flow rate in this place. So let's do the calculation first here. So 23.8 and then 1 atm, 0 Celsius, at 100 Celsius and 150 Celsius and 2.5 atm. The true volumetric flow rate is what? This is true volumetric flow rate. So let's do the calculation here first and do the conversion. Okay, so first of all, we know the standard condition of 1 kilomoles per hour will be 22.4 cubic meters here. But the thing is that in the text, they tell us the volumetric flow rate is 23.8 standard cubic meter per hour. So that means what? That means per 1 kilomole, that will be 22. And then the molar flow rate will be what? Will be 23.8 divided by 22.4, right? So this is the molar flow rate. So once we know the molar, so let's do a calculation. The molar flow rate will be what? Will be 1.06 kilomole per hour here. And once we know that this is 1.06 kilomole per hour, we immediately realize in this place, the process will be 1.06 kilomole per hour. So we realize the mass flow rate will be this. How about volumetric flow rate? We use PV equal to nRT, right? So the true volumetric flow rate will be this. And we do the calculation, bingo, we get an answer. Okay? Or you can use P1, V1 divided by T1 equal to P2, V2 equal to divided by T2, because volumetric flow rate here will be equal to the volumetric flow rate here. Okay? So you might think, well, Professor, can I use ideal gas equational state in this condition? You got me. Actually, basically, this might be not an ideal gas equational state. Okay, so this is not an ideal gas in this condition. But anyway, here we just want to let you know that you can use this method to get the volumetric flow rate. Okay, so this is one of another example, 5.2-4, is that you change from standard volumetric flow rate to true volumetric flow rate. This is one of another example. This is called methane. Methane is that this is American engineering system. Standard cubic feet per hour is 3.95 times 10 to 5th. Okay, standard cubic feet per hour. And then the temperature is this 285 Fahrenheit. And the pressure is 1.3 atm. And then now, again, we move this gas out to the flow rate meter, which is 492 Rankine, okay, and 1 atm. And we know that the volumetric flow rate here is 3.95. This is 3.95 times 10 times 5th standard cubic feet per hour. Okay, so this molar flow rate in this place will be equal to the molar flow rate in this case. So again, you use the same method and you got your answer. Okay, I don't want to waste your time here, so please do the calculation by yourself. Right, because this is relatively easy, so I go quickly. So let's go to the section 5.2c, ideal gas mixture. Before we only talk about pure gas, there's no mixture. And now let's think of the pure mixture of the gas. So ideal gas mixture, PV equal to nRT. You might have A species, B species, and C species in this container. They have their own pressure and they have their own temperature. No, they don't have their own temperature. They have their own value, the same temperature. Because temperature related to what? Kinetic energy, average kinetic energy. So there's no individual temperature, okay? So an ideal gas mixture, A, B, C substance. For example, assume there are 3 types of the molecules, or there are 3 types of species in this container. And this table telling us that how to know that a different substance, the moles and the total moles. So if we know that total mole is N, we use N stand for total mole. Then we might have Na, Nb, and Nc. So Na plus Nb plus Nc will become N total mole, right? So this is what we call the mole of the substance. A, mole of substance. B, mole of substance. C, species. How about pressure? If we use capital P, represent the total pressure, capital P, 大 P, okay? Then we use 小 p, okay? The small letter P sub A represent the pressure of A species. This represent pressure of B species. This represent pressure of C species. So you realize that's what we call this partial pressure A, partial pressure B, and partial pressure C. Okay? How about volume? If we use, so partial pressure is what? The definition of partial pressure is that the pressure that would be exerted by Na moles of the A alone. Ladies and gentlemen, remember alone. Okay, there's no B and C. That means there's no interaction because this is ideal, right? Ideal gas. Okay, there's no alone in the same value V at the same temperature T. So this is what we call partial pressure. The partial pressure is the function of what? Partial pressure is a function of a mole for species A and the volume and the temperature. Okay? And later on I will tell you an equation. So how about volume? We use capital V to represent total volume. So how about the value for the species A, value for the species B, and value for the species C? We use small letter A, V. We use small letter V to represent the species, the values represent species A, B, and C. So VA, VB, and VC. This is what we call pure component volume. So the volume, the definition of what? The definition of the pure component value is the value that would be occupied by Na moles of A alone at the total pressures P and the temperature T of the mixture. So this is a definition. Okay? And this pure component value is a function of Na mole and the pressure and the temperature. Okay? How about temperature? Temperature is T, as I just told you. Temperature is a kind of index to represent the average kinetic energy of all the molecules in the container. So there's no small temperature A, small letter A, small letter T for species A. There's no small letter T for species B, something like this. Okay. So if we have a definition like this, let's go through Dalton's law first. What's the Dalton's law? Dalton's law is that, for example, this is, we have three type of species in this container, and P times V equal to nRT. Let's regard this as equation 1. Equation 1. Okay? And then A species is sub A times V equal to nRT. This is equation 2. As I hope you still remember, as I just told you, the partial pressure A is a function of mole, volume, and the temperature. So this can be used as a kind of equation like this. So this is equation 2. So Dalton's law tells us that if you have equation 2 divided by equation 1, you can get something like this. And if you arrange this equation, you will get partial pressure A equal to molar fraction of A times total pressure. So this is what we call Dalton's law. Ladies and gentlemen, you need to remember this because this will be in your final exam. Again, partial pressure of A species equal to molar fraction A times total pressure in this environment. Not difficult at all, right? It's not difficult at all for you to remember. So Dalton's law is that if you put the A, partial pressure A and partial pressure B, C, if you have an N substance, and totally you add up all the different substances together, you know that you will get a total pressure P here. Again, this is not difficult at all for you to remember. So the definition of partial pressure of the component of an ideal gas mixture and add up to the total pressure. So what I want you to remember is this. This is important. Small capital P sub A equal to molar fraction times total pressure. Okay? Right. So Dalton's law first, and second, Amague's law. Amague's law is that, again, you have the same thing. PV equal to nRT regard as equation 1. And then P times small letter V sub A, which is what? The volume represent the species A, right? And equal to NA times RT. So again, you have equation 2 divided by equation 1. That means what? That means you have the volume of the A species equal to molar fraction of A times total volume. This is what we call Amague's law. Amague's law. Again, if you add up the value for A species, value for B species, if you add up this all together, you will get the total volume. Okay? So the total volume of the components of ideal gas mixtures add up to the total volume. Right. Are you with me so far? Yes, right? This is very easy. So I think if you don't, you are very welcome to come to me after the lecture, okay? So the expression of volume fraction and molar fraction is how to express, you have an expression of molar fraction and the volume fraction and molar fraction. For example, if you want to do the volume by weight, you have 30% weight/weight. W/W at least represent the weight fraction. Okay? And if you use volume, volume/volume, this represents volume fraction. Of course, if you use N, you use more, right? More percent represent the molar fraction. However, for the ideal gas mixture, the volume, because PV equal to nRT, right? So the molar fraction will be equal to what? Mole fraction. this fraction will equal to this fraction because this is a kind of proportional. So when we talk about this and this, when we talk about this and this, now molar fraction 30% of CH4 will be equal to the 30% of the CH4 by volume. And this is by mole. That will be the same. We just talk about the gas form, okay? Right. This is this is example 5.2-5 molecular balances on an evaporator and a compressor. And also, again, I don't have. Okay, I don't want to talk about. I don't want to read this with you, but let's think of this first. This is C3H6O in liquid, and this will fade into an evaporator. Do you know? I'm sure you know the evaporator, right? Evaporator is to make something evaporize, and it become this species become in the liquid form, become in the gas form. So this you have 400 liters per minute will be fed into this evaporator, and then you have nitrogen, which is a carrier gas, to go into this evaporator. And then another nitrogen will be fed into this joint point and go to the compressor. Okay? And then as a result, it comes out with 6.3 atm. Ladies and gentlemen, please remember this use gauge. Gauge, if you want to use PV equal to nRT, gauge pressure cannot be used. You have to add 1 atm. So that means what? If you want to use PV equal to nRT, here will be 7.3 atm. Okay, so this is gauge. If I write absolute here, that means this can be 6.3 atm can be used directly. Okay, so as it come out with 6.3 atm, and then the temperature is 325 Celsius. And then partial pressure of ACE, this is acetone actually, acetone, is 501 millimeter mercury. This is represent the pressure, right? So once you know, why they want to tell me this? Well, bingo, because this is what we call specification, because you want to know the partial pressure. You know the partial pressure. And what you know is, if you have partial pressure, you have total pressure. That means what? You can know the fraction of the acetone, right? Because according to what? According to Dalton's law. Because Dalton's law tells us partial pressure equal to molar fraction times total pressure. So you have what? Here you can realize this is one of the specifications here. Okay? Right. So molar composition of the stream leaving the question want to ask us the molar composition of the stream leaving the compressor. Here they want to know, can you get the answer of the total total volume, a total mole, and you want to know the pressure, the molar fraction of the of the acetone and the nitrogen. Can you do that? So, and another one is, what is the volumetric flow rate of the nitrogen enter to the evaporator if the temperature of the pressure and the pressure of the stream are 27 Celsius and 475 millimeter mercury gauge? So again, they tell us this condition in this stream, temperature, pressure, and then can you get other answers? Volumetric flow rate. If you want to know the volume here, then you need to know the mole first, right? If you know the mole, then you can get the answer of the volume. So again, because when we do the mass balances, we don't dealing with the volume. So let's put the unknown first. We have N1 here. So once you know this, then you can know the volumetric flow rate because you have temperature, pressure. Remember, this is gauge, okay? Temperature, pressure, mole, so you can know the volume. Okay, so you can get the answer of the second question. Okay? Okay, this is N1 over that. This is N2. And this is N3. N3 is what? N3 is called standard pressure and temperature. It's 419 cubic meter. if I give you this condition, can you tell me how many moles fed into this stream? Yes, you can, right? Because standard pressure and temperature, you have pressure, you have temperature, you have volume. So you can get this one, PV equal to nRT, right? Right? Okay, so you know you can get this answer easily. Okay, and then next is N4. N4 is total amount of this methane, acetone and nitrogen. And you want to know the fraction, which is Y sub 4, which is the fraction of the acetone, and also the fraction of the nitrogen. And because these two get together will be 1, the fraction of the acetone and fraction of the nitrogen will become 1, right? So this is 1 minus Y4. Okay, that's it. That's all information we have got. And now you realize, in order to get this Y4, we use Dalton's law, right? In order to get this N3, we use P1 V1 equal to P1 V1 T1 equal to P2 V2 T2, right? Or you can, if you understand this, you can directly convert to this, right? Because this is standard pressure and temperature. Okay, so specification and specification. So N2 here, can you get this? Can you get this number? Yes, you can, because this is acetone. So as long as you know the liter and you need to know you know the density, so you can get the moles. So this N, you can get this, right? Right? So 400 liter per minute. And this is liquid, right? So as long as you know the density and you know the weight, if you know the weight, you know the molecular weight, then you know the mole. Okay, how about N3? N3 is standard, right? So standard, do this, and we can get N3, one specification. So you have, and now once you have 5 unknowns, now you already get rid of 2 unknowns. So DOF is what? DOF is, for this, you only have 3 unknowns here. And then you want to dealing with this because this molecular species balance. So there are two species which are acetone and nitrogen, right? And divided by minus 2 and minus 1. 1 is what? Dalton's law. Dalton's law, because this one and this one, Dalton's law. So DOF will tell you 0. So you can get this easily. Okay? Please do the calculation by yourself. Okay, and then what is the volumetric flow rate of the nitrogen enter the evaporator if this blah, blah, blah. Okay, so you already know N1 and you want to know the volumetric flow rate. This is easy. So I don't want to waste your time. Please do this calculation by yourself. Right. So you might think, wow, Professor, why we need to learn this? What is evaporator and the compressor for? This is what we call heat pump. Heat pump. Heat pump is energy exchange. You know, it's like air conditioner. If you have cold water in, and you know, this is compressor. If you compress the air in, it becomes hot gas. If you have expand volume, if you have expand valve, and this hot air become cold air. So it's kind of energy exchange. Okay, this is what we call heat pump. And what is this for? This is called compressor. Okay, and this is evaporator. So the cold air go in and evaporize, become gas, and compress again. So energy, water in and water out, become hot. Okay, and cold water here. Okay, so this is what we call heat pump. That's what this is for. Okay, but we don't tell you all the cycles. We just tell you something like this, and you can do the calculation. Right. So I think I finished the section 5.2.